Hello, everyone. Hope you had a good first week of class. Here we are on Chapter 2, Chemistry of Life. I'm going to encourage everyone, again, use your reading assignment to help you get through this material. Some of these slides have a bit more information than I really would like for them to have, but chemistry can be a bit tougher than some of our other material. So let's just start. In your study guide, you're going to see it starts out with a lot of terminology. So let's go ahead and clarify from atoms to molecules what these terms mean, okay? So matter, anything that has mass and takes up space. So solid, liquid, gas, or even plasma. Elements, we know the elements from the periodic table of elements, but these are the basic building blocks of matter, and we cannot break them down by chemical means. So they are essentially set in how they are with some variations. So you might know the most common, if you will, elements that make up the human body, CNOH, so carbon, nitrogen, oxygen, and hydrogen. So you're going to see that many of the macromolecules that we talk about are going to be made up of essentially different configurations of these four elements. So here is our periodic table of elements, and you can see there's a lot of information here. So each of these rows here, 1, 2, 3, 4, essentially numbered in on the left-hand side. These are our periods, and then with Roman numerals, we are showing the groups, okay? And once you go into chemistry, you're going to learn more about the importance of groups. The periodic table is actually a very powerful way to organize and display a lot of information that we know about elements. Now you're also going to see there's an atomic number that's inside the box with the atomic symbol for the particular element, and then you're going to see the atomic mass associated with that as well. So you should take a look at that and be familiar with these terms. So an atom is the smallest unit of an element that retains its physical and chemical properties. But we can build on atoms by making molecules, so we simply bond those atoms together, and there's different kinds of bonds that we're going to go to in a little bit. Now we know that an atom is made up of sub or smaller atomic particles. In the nucleus part of the atom, we have the neutral or the neutrons. Those are uncharged subatomic particles that are making up the atom, and then we have the positively charged components, and these are called protons. The atomic number associated with an element actually tells us the number of protons. Then we have the electron shells, these orbital shells. Those are these various energy levels around the nucleus of the atom, and they themselves are containing the electrons. The electrons are negatively charged, and they're going to orbit in these shells. So this shows you some examples for hydrogen, carbon, nitrogen, and oxygen, these four elements that are the most abundant ones in the human body. And you can get an idea of their charge and their atomic mass. Okay, again, when you look at each of those rectangles on the periodic table of elements, you see the number, which is the atomic number, the atomic symbol, so the letter or letters, and the atomic mass. Okay, so isotopes essentially are atoms of the same element. So carbon is one of those. It's been really useful in studying carbon dating. We also know there's like radioactive iodine that we can use, which are a radioisotope of iodine that we can use to target abnormal cells in the thyroid gland. So essentially, isotopes are the natural variants, if you will, of the atoms of the same element. And the way that they're different is based on their neutrons. Okay, so they do differ in their atomic mass. Radioisotopes, as I mentioned with radioactive iodine or iodide, radioisotopes are unstable and they emit energy, so that energy is called radiation. Now, we know normally that radiation would be damaging to cells and can cause cancer, but we can use it actually to kill cancer cells, kill bacteria in food, We can use that to sterilize equipment like petri dishes in the microbiology lab or for imaging the body. So here we show essentially examples of using radiation, low-level radiation and MRI on the bottom figure, and then also for killing off cancer cells in the thyroid gland. Moving on to molecules and compounds. So molecules are those atoms bonded together. They can be the same atom, so think about O2, so two atoms of oxygen, or they can be different, like we have hydrogen, two atoms of hydrogen with one atom of oxygen, which makes up H2O. Now, we can build compounds, which are molecules made of different atoms. So H2O can certainly be a molecule and a compound. Oxygen can only be a molecule because its atoms bonded together. Compounds are molecules made up of different atoms. Now, when we're thinking about how do we make compounds, we're starting to talk about bonding. So we have ionic bonds and covalent bonds. So are we going to give up a bond, or are we going to share one? This is going to go more into, particularly with ionic bonding, going into those outer shells, okay? So the bonds created to fill the valence shell, so essentially what's going to happen is the atom becomes more stable by filling those shells. Atoms with more than one shell have completed their valence with 8 electrons. So if it's all filled up, then you're going to be more stable. And so this ionic bond is the attraction between a positive and negative ion. So essentially what we're going to do is either donate electrons or receive electrons to fill those shells, and we're going to create ions. So sodium chloride is the perfect example, because donating and receiving is going to allow that to be a very stable ionic bond between the sodium and the chloride. Here is a figure that's going to show you how that works. So in the sodium, in this valence shell, we see that there is an extra to donate, and it is donated to the chlorine. And so at this point in time, it becomes a chloride. The sodium is net positively charged, and now the chloride is net negatively charged because of the electron it received from the sodium. And now they're going to be bonded. Okay, covalent bonding essentially addresses when atoms share their electrons to fill their valence shells. So sharing is better. Sharing is caring. Each atom contributes 1 electron to the shared pair, and this is going to allow both of them to fill the shells and be complete, if you will. So we have a couple of conditions. You don't need to know that. So here's some examples of covalent bonding. So we have the oxygen here has 2 electrons to donate, and then we have the hydrogen here, which is going to accept it, or actually I meant to say share it. So they're sharing. Sharing is caring. That's getting a little goofy here. Same here with oxygen, is they're going to share 2 of their electrons, so now they have 4 in between them. So that's covalent bonding when they're sharing. Okay, water. So water has some very unique properties. And it has a lot to do with the electrons. So you're going to see that the electrons spend more time around the oxygen than the hydrogens, and it creates this partial negative charge on the oxygen side and a partial positive charge on the hydrogen side. So we refer to water as a polar molecule. Polar molecules are going to have some very unique properties. Don't need to see that. And one of those properties is having hydrogen bonding. So hydrogen bonds are weak bonds, and instead of showing them like we depicted earlier, we're going to show them with a dotted line. So we're going to see some of those later when we're looking at the structure of DNA. But essentially, we have an attraction between a slightly positive hydrogen to a negatively charged atom, slight negative atom, usually nitrogen and oxygen, and so we have these hydrogen bonds. So you see the little dashed lines here. These are weak bonds, but they can be super, super, super strong. Some properties that these hydrogen bonds are going to give water is that water can be a liquid at room temperature. It is going to give water the high heat capacity. And you can see there, it prevents large temperature changes in the body. So it takes a lot of heat to raise 1 gram of water, 1 degree Celsius. So in your body, it's going to be really hard to heat the water in your body. And then we have a high heat evaporation. So for hydrogen bonds to break in water, water has to boil. So that's going to be pretty hard to do in your body, but we can evaporate water from the surface of our skin, and that's going to cool us off from the evaporative property. Okay. All right. So other properties of water. Water is a really great solvent, so it dissolves many substances. The solution essentially is the solvent, which is water, and the dissolved solutes. So maybe that's salt, maybe that's potassium. It's whatever's being dissolved in the water is going to be the solute. You all learned about solutes when we talked about hypertonic and hypotonic solutions. So another way that water has some serious properties is being hydrophilic or hydrophobic. So polar molecules that attract water are called hydrophilic, but the nonpolar molecules like fatty acids and oils and fats are nonpolar. So they do not attract water. In fact, they repel water. Okay. So some other characteristics. Water has 2 really important properties, being cohesive and adhesive. So cohesion means when it wants to bond with itself. So water molecules are clinging to other water molecules through these hydrogen bonds, and they essentially go from being molecules to now being droplets of water. Then the other situation is adhesion. So that's when water is going to cling to polar surfaces like blood vessels, or like if I put a soda straw in my drink, part of my drink is going to move up into that soda straw and adhere to the inside of the straw. So this is much like the water molecules or the plasma in our blood, essentially sticking to the inside of our blood vessels and being able to be sucked along, if you will. So that is adhesion. Cohesion, being bonded to itself, and adhesion when water is attracted to other surfaces. Man, the properties of water just keep going on. Frozen water is less dense than liquid water, so that's pretty cool. Ice floats on liquid because essentially it's less dense than liquid water, and it also acts like an insulator. Our next topic are acids and bases. So acids are substances that dissociate in water, releasing hydrogen ions. So this you see is H with the net positive. And we can see that when we take things like hydrochloric acid and it dissociates, it's going to form the hydrogen protons and chloride ions. So here we have essentially an acid. Bases are essentially going to be substances that take up hydrogen ions or release hydroxide ions. So think about that. Either take up hydrogen ions or release them. So sodium hydroxide is going to be a strong base because it's dissociating into those hydroxide ions. Now, we use a pH scale to essentially measure the degree of acidity or basicity of a solution. So the range is 0 to 14. 7 is neutral in the middle. And so hydrogen ion concentration is equal to hydroxide concentration at 7. But below 7, we are going to have a much greater amount of hydrogen protons than we are hydroxide. So we are going to be acidic, but above 7, then hydroxide is going to outnumber or be greater than hydrogen. So it's the degree of each of these that's going to determine where you are at on the pH scale. This pH scale shows us from being pH of 0, like hydrochloric acid, all the way up to the very strong base, sodium hydroxide. One way to imagine some of these stronger bases is essentially they represent some of our slippery kind of chemicals, like ammonia and bleach have that kind of slippery feel to them. And then when we think about low pH, we're thinking about acids and things that can be a bit more stinging in nature, more corrosive in nature. So this is part 1 of chapter 2, and we will move on to another part